Bismillahirrahmanirrahim. Dear students, welcome to the class of electric circuit analysis. In this video we are going to solve quiz number 2. We had two questions in quiz number 2. In this video we are going to solve question number 1. Question number 1 says that determine the voltages V1 and V2 and also find the value of current I. The data we have is R1, which is 6 ohm, R2 5 ohm, R3 7 ohm, R4 6 ohm, E1 applied source is 6 volt and E2 is 18 volt. Using this data we have to find the value of V1, V2 and I, the current. So from the previous circuit we can see that R2 is parallel to R2 is in series with R3, so we can write R prime is equal to R prime is equal to R2 plus R3. By substituting the values of R2 and R3 we get R prime is equal to 12 ohms. Now we have to find the value of V2. What is the value of V2? We can see that V2 is parallel to E1, so we can say that V2 is equal to E1 because they both are in parallel, but the polarities of E1 applied force is opposite, so we can say that the value of V2 is equal to minus E1. When we substitute the value of E1 we can see that it is equal to minus 6 volt. Minus sign indicates that the value of the polarities of E is opposite, so we can say that V2 is equal to minus E1 and V2 is equal to minus 6 volt, which is our required result. Okay, now we have to find the value of V1. V1 is the voltage across resistor R1. In order to find the value of V1, we apply KVL on that loop. KVL states that sum of all the voltages rise is always equal to sum of all the voltages drop in a closed loop. So when you see there in this loop, you will see that the voltage across E1 rises, the voltage across E2 rises, but the voltage across R1 drops. So the equation of the KVL can be written as V1 is equal to E2 plus E1. V1 is basically the voltage drop across the resistor R1. E2 and E1 are the voltages rise in that loop. Substituting the values of E2 and E1, where E2 is equal to 18 volts and E1 is equal to 6 volt, we get V1 is equal to 24 volt, which is a second required value which we have to find in this question. Now we have to find the value of I. In order to find the value of I, you must need the value of I3, you need the value of I2, and you need the value of I1. We see that we have the voltages across each resistor. We have voltage across R1, we have voltage across R4, we have voltage across R prime. This is the R prime. When you have the voltages, when you have the value of the resistors, you can find the value of I3, I2 and I1. When you have these three values, you can apply KCL at that point and you will find the value of I. First we have to find the values of I1, I2 and I3. First I1, we have the value of V1 here and R1 is a resistor, so we can find the value of I1 using Ohm's law. Substituting the value in this equation, we get I1 is equal to 24 is the value of V1, 6 is the value of the resistor R1, and you will get the value of first current I1 is equal to 4 amperes. Similarly, when you are finding the value of I2, you have to know the value of V4 and R4. R4 is basically the resistor and V4 is the voltage across that resistor. You can see that R4 is parallel to E1. It means the voltage across R4 is same as the value of E1. So substituting the values, we get I2 is equal to 6 by 6, which is equal to 1 ampere. So we have the value of I1 and I2. Now we have to find the value of I3. From the circuit you will see that this is the value of, this is basically the resistor R prime. When you are finding the value of I3, you must need the value VR prime, which is also parallel to E1. So substituting the values, we get 6 by 12. 6 is basically the value of E1, which is parallel to R prime, and 12 is the value of R prime. So we get I3 is equal to 0.5 amperes. Now we have all the three values of the current, I1, I2 and I3. Now applying KCL at this point, you will see that the current entering the node is I, current leaving the node is I1, I2 and I3. So when we apply the KCL, what KCL says that sum of all the current entering the node is always equal to the current sum of all the current leaving the node. So when we apply KCL to this point, which we call K point, we get that equation I is equal to I1 plus I2 plus I3. We have all the values of I1, I2 and I3. Substituting the values into it, we get 4 ampere is the value of I1, 1 ampere is the value of I2 and 0.5 ampere is the value of I3. When we add all these three values, we get I is equal to 5.5 amperes, which is our required result. Now we see that we find the value of V1, we find the value of V2 and I. These are the required values which we have to find in that particular question. If you have any question related to this topic, you can drop a question in comment bar. Thank you very much. Dear students, welcome to ECA 1 class. Today we will discuss the nodal analysis examples. Let us consider a circuit in which we have to find the values of I1 and I2 using nodal analysis. In the first step, we have to find the nodes. You can see from the figure that we have node 1 here, node 2 here, and the reference node which is at zero potential. So in this circuit we have only two nodes, V1 and V2. So we have to find the values of V1 and V2. Now we have to apply KCL to node 1. From figure you will see that I current is entering that node, I1 is leaving that node and I3 is also leaving that node. So KCL equation can be written as I is equal to I1 plus I3. Put that equation number 1. Now what is the value of I1 and I3? From the figure you will see that the value of I1 is equal to the voltage across R1 divided by the value of R1. So I1 is equal to VR1 divided by R1. But if we place the probe of the multimeter here and here, you will see that this voltage is basically equal to V1. So we can write that VR1 is equal to V1. Now the value of I1 becomes I1 is equal to V1 divided by R1. We write that in equation number A. Similarly, we have to find the value of I3. I3 is basically equal to the voltage across resistor 3 divided by the value of that resistor. Now you will see that on R3 there are two potentials, V1 and V2. Now when we taking node 1, it means V1 is at higher potential and V2 is at lower potential. So we can write that VR3 is equal to V1 minus V2. So the current I3 is equal to V1 minus V2 divided by R3. Now substituting the values of I3 and I1 into equation number 1, you will get I is equal to V1 divided by R1 plus V1 minus V2 divided by R3. Okay, now we will simplify that equation. I is equal to V1 by R1 plus V1 by R3 minus V2 by R3. Rearranging that equation, we will get I is equal to V1 into 1 by R1 plus 1 by R3 minus V2 by R3. After substituting the values of R1, R3 and I, you will get 4 is equal to V1 into 1 by 2 plus 1 by 12 minus V2 by 12. This is basically equation of node 1. Now we have to calculate the equation of V2. Now, before applying the KCL to node 2, we will define the direction of the currents. I is basically downward direction, I2 is leaving the node, and I3 is also leaving the node. In the previous diagram, you will see that we assign the direction I3 in that way. Now, when we are taking V2 as a reference, it means if V2 is at higher potential, so the current will flow from higher to lower potential. That's why we take the direction of I3 in that direction. Now apply the KCL. When we apply KCL to that node, you will see that I is leaving the node, I2 is leaving the node, and I3 is leaving the node. So we can write the KCL equation as I plus I2 plus I3 is equal to 0, which is equation number 3. Now we have to find the values of I3 and I2. From the figure, you will see that the value of I3 is basically equals to VR3 divided by R3. Now what is VR3? VR3 have two potentials, V2 and V1. So when we are taking V2 as a reference, it means V2 is at higher potential and V1 is at lower potential. So we can write the equation of VR3 is equal to V2 minus V1. So the value of I3 is basically equals to I3 is equal to V2 minus V1 divided by R3. Name this equation as equation C. Now we have to find the value of I2. From the figure, you will see that I2 is basically equals to the voltage across R2 divided by R2. So I2 is equal to VR2 divided by R2. Now if we put probe at that point and that point, you will see that the voltage across these 2 points is basically equals to V2. So we can replace VR2 is equal to V2. Now equation for I2 becomes I2 is equal to V2 divided by R2. Name that equation as D. Now substituting the values of I2 and I3 into equation number 3, we get I plus V2 divided by R2 plus V2 minus V1 divided by R3 equals to 0. Now simplify that equation, we will get I plus V2 by R2 plus V2 by R3 minus V1 by R3. Taking V2 common from this, we will get I plus V2 into 1 by R2 plus 1 by R3 minus V1 by R3 is equal to 0. Substituting the values of R2, R3 and I, we will get 2 plus V2 into 1 by 6 plus 1 by 12 minus V1 divided by 12 is equal to 0. We name this equation as equation number 4. Basically, this is the equation of node 2 whose voltage is V2. So, by solving equation 2 and 4 by any method you have studied in the calculus, you will get the value of V1, which is equal to 6 volt, V2 which is equal to minus 6 volt. Now substituting these values of V1 and V2 into equation A, B and D, we will get the value of I1, I2 and I3. So IR1 is basically current that flows from the resistor 1, which is equal to I1. IR2 is the current that flows from the resistor R2, which is basically equals to I2. Similarly, IR3 is the current flows from the resistor 3, which is equal to I3. So these 5 values are the required values for this question. So that's all. If you have any question, please drop your question onto comment bar. Thank you very much. Dear students, welcome to ECA 1 class. Today we are going to start nodal analysis. Before going to start the nodal analysis, first we know that what is a node. Node is basically a point, a junction where multiple two or more than elements are connected with each other. That point or junction is known as node. Nodal analysis procedure. Let us see there are a few steps through which we can apply nodal analysis to any circuit. In the first step, determine the number of nodes within the network. First, we considered an example circuit. Here in the figure, you can see in the figure. Let's apply a nodal analysis. When we are going to apply nodal analysis to this circuit, we have to find a reference node and label each remaining node with a subscript value of voltage V1, V2 and so on. So from the figure, we see that V1 is basically a node where the other elements like the current source R2, R1 are connected with each other through that node. We name it V1. Now we have to select the reference node. Mostly we select a ground as a reference node. In the third step, apply Kirchhoff voltage law to each node. In our case here we have only one node, so we have to apply a Kirchhoff voltage law to that node only. Do not apply Kirchhoff law to reference node. You have to apply Kirchhoff law only to other nodes except the reference node. After applying the Kirchhoff law, you will get an equation from that node you will get that equation. Solve that equation simultaneously. If you have multiple equations, if you have one node, you have only single equation. If you have two nodes, you have two equations. Solve that equation simultaneously to get the node voltages. Let us solve a simple circuit in order to understand the nodal analysis. In this example, we have to find the values of node voltages, I1 current and I2 current. Okay, in the first step, we have to define the node voltages. So you can see from the figure that we have only a single node, so we name it V1. Now we have to define the reference node. This node, the ground node, we define it as a reference node which is equal to 0 volt. Now we have to calculate the values of V1 using that reference node. Okay, now in the second step, apply KCL to that node. You can see from the figure that this current is entering the node, this current I2 is leaving the node, and this current I1 is also leaving the node. So in the Kirchhoff current law, it states that the current entering the node must be equal to current leaving the node. So from equation 1, you can see that I1 is current that entering the node, I2 plus I1, these currents are leaving the node. So from the figure, you will see that the value of I2 is basically equal to the voltage on that resistor R2 divided by the value of R2. So we can write it I2 is equal to VR2, the voltage on the R2 divided by the value of the resistor. But from the figure, you will see that if we apply a probe at that point and that point, what is the voltage? Basically the voltage is V1, so we can write that VR2 is basically equals to V1. So equation 1 becomes I2 is equal to V1 divided by R2. We name that equation as equation number A. Similarly, for the case of I1, you will see that I1 is basically equals to VR1 divided by R1. VR1 is the voltage across resistor R1 divided by the value of the R1. Now we apply a probe at that point and at that point. So what is the value of basically VR1? VR1 is equal to V1, which is the total voltage of that branch, minus the applied source. When you minus the applied voltage, applied source from V1, you will get the value of VR1. So I1 is equal to V1 minus E divided by the value of the resistor. Substituting the value of I1 and I2 into equation 1, we get I is equal to V1 by R2 plus V1 minus E divided by R1. when we simplify this equation, you will get I is equal to V1 by R2 plus V1 by R1 minus E by R1. Now taking common V1 as a common, so you will get I is equal to V1 into 1 by R2 plus 1 by R1 minus E by R1. This is a simplified equation. Now, when we apply the values of I, R2 and R1 and E in that equation, you will get the value of V1, which is equal to 20 volts. Now we have the value of V1. Substitute that value into equation A and B to get the values of I1 and I2. So from equation A and B, you will get the values of I2. The value of I2 is equal to 1.67 ampere, and the value of I1 from equation A, I1 is equal to minus 0.67 amperes. Minus sign indicates that the direction we have assumed when we are going to solve the value of when we are going to solve that circuit, it is basically the opposite in direction. So basically the direction of I1 is in upward direction. The negative sign only indicates that the assumption is basically opposite, and this is our required result. We have to find the value of voltages via the value of I2 and the value of I1 using nodal analysis. So that's all for today's lecture. If you have any question, please drop your comment in comment box. Thank you very much. Dear students, welcome to ECA1 class. Today we are going to discuss substitution theorem. Substitution theorem states that if the voltage across and the current through any branch of a DC bilateral network are known, this branch can be replaced by any combination of elements that will maintain the same voltage across and the current through the chosen branch. So, in order to understand the substitution theorem, let us take an example. We know the value of current through this branch from A to B is 3 ampere, and the voltage across these 2 points A and B is 12 volt. Now we can replace this branch with any given circuit. So we can replace it with a 12 volt voltage source having 3 ampere current flowing from A to B, or you can replace this branch with a 3 ampere current source and the voltage across A and B is 12 volt, or you can replace it with the voltage source of 6 volt with series resistor of 2 ohms, or you can replace this branch with a current source in parallel with the 12 ohm resistor with the voltage of 12 volt. So you can replace this A and B point with any of these circuit, you will get the same result. This is basically the substitution theorem. Now this figure demonstrates the effect of knowing a voltage at same point in a complex circuit. If we know the voltage across A and B, you can replace this whole circuit with that voltage source. In the second figure demonstrates the effect of knowing the current at same point in a complex circuit. If we are going to replace this branch with a current circuit, you can replace this whole circuit with the current source by finding the value of that current. So this is basically the substitution method, that you know the voltage across the branch, you can replace it with the voltage source, and if you know the current across this point, you can replace it with the current source. So that's all for today's lecture. If you have any question, kindly comment it into comment box. Thank you very much. Dear students, welcome to ECA1 class. Today we will discuss Millman theorem. Millman theorem states that if you have any number of parallel voltage sources, that can be reduced to 1. For example, if we have 3 voltage sources of different values, in parallel, you can replace it with a single voltage source and a single equivalent resistance. These resistors are basically internal resistance of that voltage sources. So according to the Millman, you can replace all these sources, parallel voltage sources, to one single voltage source. Now let's discuss the Millman theorem procedure. First of all, for example, if we have three different sources in parallel, E1, E2, E3, with the parallel resistors R1, R2 and R3, in the first step, convert all the voltage sources to the current source using source transformation theory. So when we replace this voltage source with the current source, you will see that using Ohm's law, we will write the value of the current is I1 is equal to E1 divided by R1. If we write this in term of conductance, you can write the value of I1 is equal to E1 into G1. G1 is the basically conductance, which is reciprocal of the resistance. Similarly, you can replace the second source, voltage source, to the current source, and the third one is also with the current source. In the second step, combine all these parallel sources. You will see that the direction of the current is upward. In this case, the direction of the current is also upward, and in the third source, the direction of the current is also in the upward direction. So if we consider this is a node, you will see that I1 is entering the node, I2 is also entering the node, and I3 is also entering the node. So we can replace these three current sources with IT, which is equal to I1 plus I2 plus I3. Similarly, G1, G2 and G3 are in parallel, so we can write the total conductance as GT. Now you will see that we have a simple current source here in this circuit. Now in the third step, convert the resulting current source to voltage source and the desired single source network is obtained. You can convert that current source to the voltage source, and you will see that you have replaced the three different voltage sources to a single voltage source with a single internal resistance. Let us more simplify the Millman theory using generalized equation. If you want to find the E equivalent of the different voltage sources, we will write the equation as E is equal to I by GT. GT is the basically total conductance of the circuit. Now, if you have multiple current sources in the circuit and multiple current internal resistance of that sources, you can write the equation as I1 plus minus I2 plus minus I3 plus minus I up to plus minus IN. Similarly, for the conductance, G1 plus G2 plus G3 up to n number of conductance. Plus minus sign indicates the direction of the current, either it is in upward direction or in the downward direction. Either they are entering the node or they leaving the node. So we can write that equation in the form of E equivalent is equal to plus minus E1 G1. Basically E1 G1 is the equation of I1, E2 G2 is the equation of I2. These equations are in term of conductance. Similarly, R equivalent is equal to 1 by GT, because conductance is the reciprocal of the resistor, so we can write it 1 by G1 plus G2 plus G3 up to Gn. Now if we write these equations of a single voltage source and a single internal resistance in term of resistance, we can write it as E equivalent is equal to E1 by R1, which is the equation of I1, E2 by R2, which is the equation of I2, similarly I3 and IN. So the value of G1 is 1 by R1, 1 by R2 plus 1 by R3. We can write these equation in term of resistance. Similarly, R equivalent is equal to, this is basically the formula of the resistor in parallel, 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by Rn. Now let us solve an example in order to understand the Millman theorem. Using Millman theorem, find the current through and voltage across the resistor RL. We have to find the value of the current through RL and the voltage across that load resistance. You can see from the figure that we have three voltage sources of the different values in parallel with these three resistors. Now in the first step, we have to find the value of E equivalent. E equivalent is equal to E1 by R1 minus E2 by R2 minus sign is because of that polarity of E2. Similarly, R1 is 5 ohm, R2 is 4 ohms, R3 is 2 ohms. Substituting the value in this equation, you will get the value of E equivalent, which is equal to 2.11 volts. In the second step, we have to find the value of R equivalent from R1, R2 and R3. R equivalent is equal to 1 divided by 1 by R1 plus 1 by R2 plus 1 by R3. This is basically the relation of the resistors in parallel. So when we substitute the values, we will get the value of R equivalent, which is equal to 1.05 ohms. Now we have the value of E equivalent, we have the value of R equivalent. Now we can find the value of VL and IL through RL. Now you can see from the figure that this is simple series circuit. Now from the figure you will see that it is a simple series circuit. Now when we are going to find the value of IL, IL is basically equal to V by RT. RT is the total resistance of the circuit which consists of R equivalent and RL. IL is equal to total voltage, which is 2.11 divided by the total resistance. Total resistance consists of R equivalent and RL. So from when we substitute the values, we will get the value of IL, which is equal to 0.52 amperes. Now voltage, if we have the value of the current, we have the value of the resistor, you can find the value of voltage, which is equal to IL into RL. So when we substitute the values, we will get the value of VL, which is equal to 1.56 volt. So this is basically the Millman equivalent circuit. So in order to apply the Millman, you must need two values, the value of E equivalent and the value of R equivalent. So you have to remember the two relations of E equivalent and R equivalent to apply Millman theorem to any circuit which consists of voltage sources of different values in parallel with their internal resistances. So that's all for today's lecture. If you have any question, comment in comment bar. Thank you very much. Dear students, welcome to ECA 1 class. Today we will discuss maximum power transfer theorem. When designing a circuit, it is often important to answer few questions. Number one is, what load should be able to a system to ensure that the load is receiving maximum power from the system or not? Or for a particular load, what condition should be imposed on the source to ensure that it will deliver the maximum power available? Fortunately, the process of finding the load that will receive maximum power from a particular system is quite straightforward due to maximum power transfer theorem, which states that the load will receive maximum power from a network when its resistance is exactly equal to the Thevenin resistance of the network applied to the load. So we say that when load resistor is equal to the Thevenin resistance, it means the maximum power is delivered. From the figure you will see that this shaded region is basically Thevenin equivalent circuit, in which this resistor is basically R Thevenin. When this R Thevenin is equal to that load resistor, we say that the maximum power is being delivered. From this figure you will see that this is simple series circuit. So when we calculate the current of the series circuit, or the current from the load resistor, is equal to total voltage, which is E Thevenin, divided by total resistance of the circuit. Total resistance of the circuit is basically R Thevenin and RL. So when we are dealing with the maximum power transfer, so RL is equal to R Thevenin, so we can replace it E Thevenin divided by R Thevenin plus R Thevenin. So current from the load resistor is basically equal to total voltage divided by 2 times of the R Thevenin. Now using the power relation and substitute the values, we will get PL is equal to IL square into RL, which is equal to E Thevenin divided by 2 R Thevenin whole square multiplied by R Thevenin, because RL is equal to R Thevenin, which is equal to E Thevenin square into R Thevenin divided by 4 into R Thevenin square. This R Thevenin will be cancelled out with that square term. So the load power of the load is equal to E Thevenin square divided by 4 times of the R Thevenin. This is basically the maximum power delivered to the load resistor. Let us take an example to verify that the maximum power is delivered when RThevenin is equal to load resistor. E Thevenin is equal to 60 volt, RThevenin is equal to 9 volt, and load resistor is basically a variable load resistor. So when we find the value of the current, which is equal to E Thevenin divided by RThevenin plus RL, substituting the value of E Thevenin and RThevenin, we get 60 volt divided by 9 ohm plus RL. RL is basically a variable resistor. So VL is equal to RL into E Thevenin divided by RL plus R Thevenin, which is equal to RL into 60 divided by RL plus R Thevenin. Now the power is equal to IL square into RL, which is equal to 60 volt divided by 9 ohm plus RL whole square into RL, which is equal to 3600 RL divided by 9 plus RL whole square. Now we substitute the values of RL randomly and we will see that we have this thing. Now you will see that RL, when we vary RL 0.1, 0.2, 0.5, 1, 2, 3, 4 up to 1000 ohm, the power is changing. Now at this point, when RL is equal to R Thevenin, which is equal to 9 ohm, you will see that 100 watt power is delivered. From this graph, you will see that if we go if we change the RL greater than the R Thevenin, the power is decreasing. If we decrease the value of RL from R Thevenin, the power is also decreased. So when R Thevenin is equal to RL, the maximum power is delivered at that time. The operating frequency is defined as the ratio of the power delivered to the load PL to the power delivered by the source. So percentage efficiency is equal to PL, power delivered to the load, divided by power delivered by the source into 100. When R Thevenin is equal to RL, we will see that the efficiency is equal to IL square divided by RL divided by IL square into RT into 100. RL divided by RT, because IL square will be cancelled out. We will get R Thevenin divided by R Thevenin plus R Thevenin. So when we substitute the value, we simplify this equation, we will get the percentage efficiency of operating efficiency for maximum power delivered. The maximum power theorem is equal to 50%. So this is the maximum efficiency for maximum power transfer theorem. That's all for today. If you have any question, comment in comment box. Thank you very much. Dear students, welcome to ECA class. Today we will discuss the superposition theorem example. Let us consider a circuit in which we have to find the value of I2, which is flowing from the resistor R2 using superposition theorem. So using superposition theorem, now we take only one source. Let us consider that current source in the circuit and remove the voltage source. We can remove our voltage source using a short circuit. When we short circuit the voltage source, we redraw the circuit in this form. Now we have to find the value of I2 prime, which is flowing in downward direction. Now you can see that if we apply current divider rule at this point, we will find the value of I2 prime, which is equal to R1 into I divided by R1 plus R2. Substituting the values, we will get the value of I2 prime, which is equal to 2 milliamperes. In the second part, now we consider a voltage source and remove the current source. Now when we are going to remove the current source, we replace it with an open circuit. Now when we redraw this circuit, you will get the circuit of this form. Now you will see that this part of the circuit is basically in series. So in the series, when we have to find the value of the current, now I2 double prime is equal to E divided by the total resistance of that circuit. We are considering this part of the circuit because I2 prime is flowing in this part of the circuit. Now when we substitute the values of E, R1 and R2, we will get the value of I2 double prime, which is equal to 0.5 milliampere. Now from the both figures, you will see that I2 prime is flowing downward direction. Similarly, I2 double prime is also flowing in downward direction. The direction of the current is same. So the total current I2 is equal to I2 prime plus I2 double prime. When you substitute the values, 2 milliampere is the value of I2 prime and 0.5 milliampere is the value of I22 prime, we will get the total current flowing through that resistor, which is equal to 2.5 milliampere, which is our required result. Thank you very much. Hope this example is very useful for you to understand the superposition theorem. In case of any question, please drop your question in comment bar. Thank you very much. Dear students, welcome to ECA 1 lecture. The topic of today's discussion is superposition theorem. Superposition theorem basically used for analyzing the network that have two or more sources that are not in series or parallel. It reveals the effect of each source on a particular quantity of interest. For the sources of different type, which affect the parameters of the network in a different manner, and apply a separate analysis for each type, with the total result simply the algebraic sum of the result. So we can define the superposition theorem as the current through or voltage across any element of a network is equal to the algebraic sum of the current or voltage produced independently by each source. Since the effect of each source will be determined independently, the number of networks to be analyzed will equal to the number of sources. It means that if we have two or more than two sources in the network, so we have to analyze our whole network equal to the number of sources. For example, if we have two sources in the network, we have to analyze our network 2 times. If we have 3 sources in our network, we have to analyze our network 3 times. Superposition theorem is not applicable to the power level. In our case, in our example, we will see that the superposition theorem is not applicable to power levels. If we have multiple sources in our network, we have to take one source at a time and remove the other sources. When removing a voltage source from a network schematic, replace it with a direct connection, or we say that with a short circuit of 0 ohms. Any internal resistance associated with the source must remain in the network. From the figure, you will see that if we are going to remove this voltage source, we have to replace it with the short circuit, but the internal resistance of that source remain on its position. Now if when we are removing a current source from a network replaced by an open circuit of infinite ohms, any internal resistance associated with the source must remain in the network. From the figure you will see that we have that current source I. When we are going to remove that current source, we replace this current source with an open circuit, but the internal resistance remain on its position. In order to understand the superposition theorem, let us solve an example. In this example, we have to find the current through the resistor R2 and also demonstrate the superposition theorem is not applicable to the power level. So we have to find the value of I2 which is flowing from the resistor R2 because of that source and that source, so voltage source and the current source, using superposition theorem. In the first step, we have to take only one source. So we take a voltage source and remove the current source. We remove the current source by replacing it by an open circuit. Now from the figure you will see that when we remove the current source from the network, it becomes a simple series circuit. So the current through IR2 is basically I prime by I prime 2. I prime 2 stands for it is because of the first source. So the value of the current is basically equal to E by RT. E is the total voltage, RT is the total resistance of that circuit. So E is I2 prime is equal to E divided by R1 plus R2. When we substitute the values of R1, R2 and E, we will get 36 volts is basically value of E, 12 is the value of R1 and 6 ohm is the value of R2. We will get the value of I2 prime which is equal to 2 ampere, and you will see from the figure that this 2 ampere current is flowing down in downward direction. Now in the second step, we take a current source and remove the voltage source, and when we are going to remove the voltage source, we replace it with the short circuit. Now you see from the figure that R2 and R1 are in parallel, and I2 double prime is the current flowing from R2 because of that current source. So when we apply current divider rule here, we will get I2 double prime is equal to R1 into total current divided by total resistance of the circuit. When we substitute the value of R1, R2 and I, we will get I2 double prime is equal to 6 ampere. Now from the figure you will see that this I2 double prime is flowing in the downward direction. So both the currents are flowing in the downward direction. Using these two figures, we will see that I2 is basically I2 prime plus I2 double prime, because due to that voltage source, I2 prime current is flowing in downward direction. Due to that current source, I2 double prime current is also flowing in downward direction. So the direction of both the current is same. So the net current is equal to I2 prime plus I2 double prime. The value of I2 prime is 2 ampere and I2 double prime is 6 ampere. So the total current I2 flowing from resistor R2 is basically equals to 8 amperes. Now solving for the second part of the question, power levels. From the figure you will see that the I2 current is flowing in the downward direction, which is equal to 2 ampere. So the power is equal to I2 prime square into R2, which is equal to 24 watts. Now when we take a current source, you will see that the current flowing I2 double prime in the downward direction is basically equals to 6 ampere. So when we substitute the values in the power relation, we will get the value 216 watt. So the net power because of these two currents is equal to 240 watts. P1 plus P2, P1 is equal to 24 watt and P2 is equal to 216 watt. The total power is equal to 240 watts. Now using the superposition theorem, we see that the current flowing from R2 is equal to 8 ampere because of the both sources. So when we calculate the power using 8 ampere current, you will see that the total power is equal to 380 watts. Now we see that due to the power due to the individual sources is equal to 240 watts, but the total power dissipated by this resistor is equal to 348 watt. So it means that the power the superposition theorem is not applicable to the power levels, because the individual power, the sum of the individual power is not equal to the total power. That's all. If you have any question, please drop your question in comment box. Thank you very much. Dear students, welcome to ECA 1 class. In today's class, we will discuss the conversion between the Norton and the Thevenin equivalent circuit. That how you can convert Norton equivalent circuit to Thevenin equivalent circuit and Thevenin equivalent circuit to Norton equivalent circuit. Thevenin equivalent circuit can be converted to Norton equivalent circuit, and Norton equivalent circuit can be converted into Thevenin equivalent circuit by simply using Ohm's law. For example, if we have that Thevenin network and we have to convert into the Norton equivalent, you will see that R Thevenin is equal to R Norton and E Thevenin is equal to I Norton into R Norton. This is basically the Ohm's law. V is equal to IR. Since IN is equal to E Thevenin divided by R Thevenin and R Norton is equal to R Thevenin. So when we have to convert that Thevenin equivalent circuit to Norton equivalent circuit, we have to find the value of IN, because in Norton we have current source and in Thevenin we have voltage source. If we have Norton equivalent circuit, we have to find the value of E Thevenin by using Ohm's law. R Thevenin is always equal to R Norton and R Norton is always equal to R Thevenin. Let us consider an example in which we have that Norton equivalent circuit and we have to convert it to the Thevenin equivalent circuit. From the Norton equivalent circuit, you will see that we have I Norton which is equal to 3 ampere and R Norton which is equal to 2 ohms. Now we have to find E Thevenin and R Thevenin. So we know that R Norton is equal to R Thevenin, so the value of R Thevenin is 2 ohms. Now we have to find the value of E Thevenin. So using Ohm's law, E Thevenin is equal to I Norton into R Norton. The value of I Norton is basically equal to 3 ampere. So substitute the values here. We see that I Norton is equal to 3 ampere and R Norton is equal to 2 ampere. So E Thevenin is equal to 6 volt. Now this is the equivalent Thevenin circuit. So you have converted the Norton equivalent circuit into the Thevenin equivalent circuit using simple Ohm's law. Now when we have to convert that Thevenin circuit to that Norton equivalent, we will convert it like that. R Thevenin is equal to R Norton, so the value of R Norton is equal to 2 ohms. Now E Thevenin is equal to 6 volt. We have to find the value of IN, so IN is equal to E Thevenin divided by RN, which is equal to 3 ampere. So by using Ohm's law, you can convert Norton equivalent circuit to Thevenin and Thevenin equivalent circuit to Norton equivalent circuit. So that's all. If you have any question, drop your question to comment box. Thank you very much. Dear students, welcome to ECA 1 class. Today we are going to discuss Norton theorem. In the previous lecture, we studied Thevenin theorem, in which we state that any two-terminal DC network can be replaced by an equivalent circuit consisting of solely of a voltage source and a series resistor. In Norton theorem, we have any two-terminal DC network can be replaced by an equivalent circuit consisting solely of a current source and a parallel resistor. Here is the difference between the Thevenin and the Norton is that Thevenin is basically dealing with the voltages and current and the resistor in the series, but in Norton theorem we are dealing with the current source with a parallel resistor. Now let's see the procedure for applying Norton theorem to any electrical circuit. In the first step, let us consider an example with a voltage source and the two resistors. We have RL load resistor. We have to find the Norton equivalent circuit for that shaded region. In the first step, remove the portion of the network where the Norton equivalent circuit is found. Remove RL temporarily from the network. You can see in the figure we have removed RL from the network, and now we have to find the Norton equivalent for that particular circuit. In the second step, mark the terminals of the remaining two terminal network. We marked here A and B. Find Rn. Rn is basically Norton resistance. Calculate Norton resistance by first setting all the sources to 0. All the sources to 0 means if you have a voltage sources in circuit, replace that voltage source with a short circuit. And if you have a current source in the circuit, replace that current source with an open circuit. In our case, we have only one voltage source E1, so we replace that voltage source with the short circuit. Here you can see in the figure we have replaced the voltage source with a short circuit. Now we have to find the Norton resistance. Now from the figure you will see that R2 and R1 both are in parallel, so the Norton resistance is basically equal to R1 parallel to R2. In the next step, we have to find the Norton current. Calculate Norton current by first returning all sources to their original position and finding the short circuit current between the marked point. From the figure you will see that the marked points are A and B. We have to find I Norton from that point in order to find the equivalent Norton circuit. Draw the Thevenin equivalent circuit with the portion of the circuit previously removed replaced between the terminal of the resistor RL. So this is basically the Norton equivalent circuit for that shaded region. Okay, now let us solve an example in order to understand how we can apply Norton theorem to any circuit. In this circuit, we have to find the Norton equivalent circuit for that shaded region. In the first step, we remove that RL from the circuit temporarily and mark that point with A and B. In the second step, we have to find the Norton resistance Rn. So in order to find the Norton resistance, we have to set all the sources to 0. In this case, we have only a single voltage source, so we replaced it with a short circuit. Now you will see that R1 and R2 basically are in parallel combination, so Rn is equal to R1 parallel to R2. When we put the values of R1 and R2 in the relation, we get the value of Norton resistance, which is equal to 2 ohms. Now in the second step, we have to find the Norton current. So in order to find the Norton current, short circuit that 2 points A and B and find the current through that short circuit. So we set all the sources to their original position, and from the circuit you will see that all the current will flow through that short circuit and no current will flow through R2. It means we have to remove R2 from the circuit because current follows the easiest path. So easiest path is basically A and B, which is short circuit. So we have a simple series circuit with a voltage source 9 volt and R1. So the current through the circuit is basically equals to the applied voltage divided by the total resistance. In this case, when this point becomes short, R2 to have no effect on the circuit, so we remove R2 from the circuit. So we have only R1. So when we substitute the values into the relation, we get I Norton, which is equal to 3 amperes. Now we have R Norton and I Norton. We can find the Norton equivalent circuit for that shaded region. So this is basically the Norton equivalent for that particular circuit. We have a current source with the value of 3 ampere and the parallel resistance Rn, which is equal to 2 ohm. Place your load resistor to its original position. That's all for today's lecture. Thank you very much. If you have any questions, you can ask through comment box. Thank you. Dear students, welcome to ECA 1 class. In this video, we will discuss the Thevenin theorem examples. In this example, we have to find the Thevenin equivalent circuit for the network in the shaded area of the braid network. We have to find Thevenin equivalent circuit between these 2 points A and B. In the first step, replace load resistor from A and B point. Now in order to find R Thevenin between these 2 points, we have to remove that voltage source with a short circuit. So we replace that voltage source with a short circuit. Now you can see from circuit that R1 is basically parallel to R3 and R2 is parallel to R4. When we redraw this circuit, it looks like this. R3 is parallel to R1, R4 is parallel to R2. So R Thevenin is equal to the resistance between A and B is equal to R1 parallel to R3 plus R2 parallel to R4. When we substitute the values of R1, R3, R2, R4 in the parallel combination, we will get the value of R Thevenin, which is equal to 5 ohms. Now in the second step, we have to find the value of V E Thevenin. So from the figure you will see that if we apply KVL to this loop, we will find the value of E Thevenin. But first we need the value of V1 and V2. When we have the value of V1 and V2, applying KVL to this loop, we will get the value of E Thevenin. Now from the figure you will see that this E is basically parallel to these 2 resistors and it is parallel to these 2 resistors also. So the value of the voltage at this point is basically equal to 72 volt and also at this point is 72 volts. So first we apply VDR to this loop in order to find the value of V1. So V1 is equal to R1E divided by R1 plus R3. Substituting the values, we will get the value of V1, which is equal to 48 volts. We get 48 volts. Now we apply KVL, voltage divided rule, to this loop in order to get the value of V2. So V2 is equal to R2E divided by R2 plus R4. Substituting the values, we get the value of V2, which is equal to 54 volts. Now, applying KVL to this loop, because we have the value of V1 and V2. When we apply KVL, we see that E Thevenin plus V1 minus V2 is equal to 0. Substituting the values, we get the value of E Thevenin, which is equal to 6 volt. Now we have R Thevenin and E Thevenin, so we can redraw our circuit or Thevenin. So we have a Thevenin equivalent circuit for this shaded region, in which we have only a voltage source and a series resistor. Placed load resistor to its original position between the points A and B. That is our equivalent circuit for that shaded region. So in the next example, we have to find the Thevenin equivalent circuit for the network in the shaded region. R is the load resistor across which we have to find the Thevenin equivalent circuit. In the first step, remove RL from point A and B. Now we have to find our Thevenin, so we have to set the voltage sources to 0 and replace all these sources with the short circuit. Now you will see that R3, R2, R1 are in parallel combination with R4 in series when we are going to find out R Thevenin. So R Thevenin is basically equal to R4 plus R1 parallel to R2 parallel to R3. So we get the value of R Thevenin is equal to 2 kilo ohms. Now in the second step, we have to find the value of E Thevenin, which is basically the open circuit voltage between A and B point. Now from the figure you will see that we have two voltage sources, so apply superposition theorem to find the value of E Thevenin. So first we have to take only a single source E1 and short the other voltage source. Now we have to find that open circuit voltage at point A and B. So E Thevenin is basically equal to the voltage across R3 because R3 is parallel to that point. Here R4 is considered to be equal to 0 because no current is flowing in this resistor because of that open circuit. That's why V4 is equal to 0. So RT, the total resistance of this circuit, is equal to R2 parallel to R3. When we solve it, it becomes a series circuit, and when we apply voltage divider rule at that point, we will get the value of V3, which is equal to E Thevenin prime. So V3 is equal to R prime T, which is 2.4 kilo ohm, into E1 divided by R prime T, which is equal to 2.4 kilo ohm. When we substitute the values, we get the value of E Thevenin prime, which is equal to 4.5 volts. Now consider E2 source and set E1 as 0 with an short circuit. So when we see the circuit, we have to find the value of E Thevenin double prime at this point. Now same is the case here. R4 is considered to be 0 because no current is flowing into this circuit, into this resistor, due to that open circuit. So E Thevenin is basically equal to V3 because V3 is parallel to E Thevenin. So R prime T is equal to R1, which is parallel to R3, which is equal to 0.706 kilo ohms. So apply VDR to the simple circuit when we have two resistors. V3 is equal to R prime T E2 divided by R prime T plus R2. When we substitute the values, we get the value of V3, which is equal to 1.5 volts. V3 is basically equal to E Thevenin double prime, which is equal to 1.5 volt. Now we have the voltage E Thevenin prime and E Thevenin double prime. So the net E Thevenin is equal to E Thevenin single prime minus E Thevenin double prime. The value of E Thevenin single prime is 4.5 volt and E Thevenin double prime is 1.5 volt. The net E Thevenin is equal to 3 volts. The polarity of E Thevenin single prime is used. So this is our equivalent Thevenin circuit for the shaded region. place your load resistor to its original position between A and B. That's all for today's lecture. If you have any question, comment in comment bar. Thank you very much. Dear students, welcome to ECA 1 class. Today we will going to discuss Thevenin theorem. So far, we have presented a number of techniques for circuit analysis. At this point, we will add one new theorem to our collection of tools that will prove to be extremely useful. The theorem is named after their author Emile Thevenin, a French engineer. Suppose that we are given a circuit and that we wish to find the current, voltage or power that is delivered to some resistor of the network, which we will call the load. Thevenin theorem tells us that we can replace the entire network exclusive of the load by an equivalent circuit that contains only an independent voltage source in series with a resistor in such a way that the current voltage relationship at the load is unchanged. So we say that any two-terminal DC network can be replaced by an equivalent circuit consisting solely of a voltage source and a series resistor. Now let's see what are the procedure to apply Thevenin theorem to any circuit. Let us consider a circuit in which we have to find the Thevenin equivalent for this shaded region. In the first step, remove the portion of the network where the Thevenin equivalent is found. In our case, remove RL temporarily from the network. So we have to remove that RL from the network in order to find a Thevenin equivalent circuit for that shaded region. So when we remove RL, the circuit looks like this. In the second step, mark the terminals of the remaining 2 points. So we mark A and B where RL exists. Now we have to find the R Thevenin resistance. In order to find the R Thevenin, set all the sources equal to 0. Sources equal to 0 means if you have a voltage sources in the circuit, replace it with the short circuit, and if you have any current source in the circuit, replace it with the open circuit. So here we have to find R Thevenin by short circuiting this voltage source. In next step, we have to find the value of E Thevenin, means Thevenin voltage. In order to find the value of E Thevenin, returning all the sources to their original position and finding the open circuit voltage between the marked terminal. We have to find the voltage at A and B point. In this case, you will see that the voltage across R2 is basically equal to that voltage which is across point A and B. After that, when you find R Thevenin and E Thevenin, draw the Thevenin equivalent circuit with the portion of the circuit previously removed or replaced between the terminal of the resistors. So here we place the Thevenin voltage and a Thevenin resistance. So this is basically the equivalent Thevenin circuit for this shaded region. RL is placed on its original position. Now, in order to understand the Thevenin theorem, let us take an example. In this example, we have to find the Thevenin equivalent circuit for the given network in the shaded region. We have to find the Thevenin equivalent for this region. So, in the first step, remove that RL road resistor because we have to find the Thevenin equivalent for this shaded region. When we remove RL, mark these points A and B. Now we have to find the value of R Thevenin. So when we are going to find R Thevenin, we have to set our sources to 0. In our case, we have only a single voltage source. So when we are going to set this source to 0, remove that source with the short circuit. So now you can see that this R1 and R2 are in parallel to each other. So R Thevenin is equal to R1 parallel to R2. When we substitute the values, we will see that 3 into 6 divided by 3 plus 6 is equal to 2 ohms. So the value of R Thevenin is equal to 2 ohms. In next step, we have to find the value of E Thevenin. So E Thevenin basically is the voltage at this point A and B. It is basically an open circuit voltage at that point from where we remove that load resistance. Now from the figure you will see that this A and B point is parallel to this R2. It means the voltage on R2 is basically equal to the voltage at A and B point, which is equal to E Thevenin. So from the circuit we see that it is basically a simple series circuit. So when we applied voltage divider rule to this circuit, we will get that will give E Thevenin is equal to R2 into E1 divided by the total resistance of that series circuit. When we substitute the values of R2, R1 and E into this equation, we will get E Thevenin is equal to 6 volt. Now for Thevenin theorem, we just need the value of R Thevenin and E Thevenin. So from these two values, we will find the equivalent Thevenin circuit. So from the circuit, we will see that this is the value of E Thevenin and this is the value of R Thevenin. We replace this shaded region with this voltage source and series resistors. Now place the load resistance to its original position. Now you will see that the behavior of these two elements is equal to this whole shaded circuit. This is basically the Thevenin equivalent circuit for that shaded region. That's all for today. If you have any confusion, comment your question in comment box. Thank you very much. Bismillahirrahmanirrahim. Dear students, welcome to the class of electric circuit analysis. In this video we are going to solve quiz number 2. We had 2 questions in quiz number 2. In this video we are going to solve question number 1. Question number 1 says that determine the voltages V1 and V2 and also find the value of current I. The data we have is R1, which is 6 ohm, R2 5 ohm, R3 7 ohm, R4 6 ohm, E1 applied source is 6 volt and E2 is 18 volt. Using this data we have to find the value of V1, V2 and I, the current. So from the previous circuit we can see that R2 is parallel to R2 is in series with R3. So we can write R prime is equal to R prime is equal to R2 plus R3. By substituting the values of R2 and R3, we get R prime is equal to 12 ohms. Now we have to find the value of V2. What is the value of V2? We can see that V2 is parallel to E1. So we can say that V2 is equal to E1 because they both are in parallel. But the polarities of E1 applied force is opposite. So we can say that the value of V2 is equal to minus E1. When we substitute the value of E1, we can see that it is equal to minus 6 volt. Minus sign indicates that the value of the polarities of E is opposite. So we can say that V2 is equal to minus E1 and V2 is equal to minus 6 volt, which is our required result. Okay, now we have to find the value of V1. V1 is the voltage across resistor R1. In order to find the value of V1, we apply KVL on that loop. KVL states that sum of all the voltages rise is always equal to sum of all the voltages drop in a closed loop. So when you see there in this loop, you will see that the voltage across E1 rises, the voltage across E2 rises, but the voltage across R1 drops. So the equation of the KVL can be written as V1 is equal to E2 plus E1. V1 is basically the voltage drop across the resistor R1. E2 and E1 are the voltages rise in that loop. Substituting the values of E2 and E1, where E2 is equal to 18 volts and E1 is equal to 6 volt, we get V1 is equal to 24 volt, which is a second required value which we have to find in this question. Now we have to find the value of I. In order to find the value of I, you must need the value of I3, you need the value of I2, and you need the value of I1. We see that we have the voltages across each resistor. We have voltage across R1, we have voltage across R4, we have voltage across R prime. This is the R prime. When you have the voltages, when you have the value of the resistors, you can find the value of I3, I2, and I1. When you have these three values, you can apply KCL at that point and you will find the value of I. First we have to find the values of I1, I2 and I3. First, I1, we have the value of V1 here, and R1 is a resistor, so we can find the value of I1 using Ohm's law. Substituting the value in this equation, we get I1 is equal to 24 is the value of V1, 6 is the value of the resistor R1, and you will get the value of first current I1 is equal to 4 amperes. Similarly, when you are finding the value of I2, you have to know the value of V4 and R4. R4 is basically the resistor and V4 is the voltage across that resistor. You can see that R4 is parallel to E1. It means the voltage across R4 is same as the value of E1. So substituting the values, we get I2 is equal to 6 by 6, which is equal to 1 ampere. So we have the value of I1 and I2. Now we have to find the value of I3. From the circuit you will see that this is the value of, this is basically the resistor R prime. When you are finding the value of I3, you must need the value VR prime, which is also parallel to E1. So substituting the values, we get 6 by 12. 6 is basically the value of E1, which is parallel to R prime, and 12 is the value of R prime. So we get I3 is equal to 0.5 amperes. Now we have all the three values of the current I1, I2 and I3. Now applying KCL at this point, you will see that the current entering the node is I, current leaving the node is I1, I2 and I3. So when we apply the KCL, what KCL says that sum of all the current entering the node is always equal to the current sum of all the current leaving the node. So when we apply KCL to this point, which we call K point, we get that equation I is equal to I1 plus I2 plus I3. We have all the values of I1, I2 and I3. Substituting the values into it, we get 4 ampere is the value of I1, 1 ampere is the value of I2 and 0.5 ampere is the value of I3. When we add all these three values, we get I is equal to 5.5 amperes, which is our required result. Now we see that we find the value of V1, we find the value of V2 and I. These are the required values which we have to find in that particular question. If you have any question related to this topic, you can drop a question in comment bar. Thank you very much.